So inference. Inference is about inferring from a sample to the population it was drawn from. So for example, if you sample houses in the Kitchener-Waterloo area, then the population is all the houses in the Kitchener-Waterloo area. We have the regression here that are the true values, but they are unknown. This is the regression line that you would get if you actually had the data for all the houses in Kitchener-Waterloo, not just the sample. So there is a value for beta 0, which is the true value, the regression on everything, but we don't know what the value is because we don't have the whole population, we just have a sample. Likewise, the epsilon i's here are the true value. The true residuals. They are unknown, but they're not random, they're fixed, right? They're just unknown. By contrast, based on the sample, we have the estimated quantity. And so I have the estimated betas, and I have the estimated residuals. I didn't need to put a hat over here, unless I wanted to also predict additional houses that were not in my sample. So because in the sample I have the true ones, right? So these are estimated, and that's why I have a hat over here. I don't distinguish in my notation between an estimator and an estimate. An estimator is the formula, and then once you have a sample and plug the values of the sample into the formula, you have estimated values. It's usually clear from the context what it is. So yeah. We will also need the chi-square distribution in just a little bit, so I'm reminding you of the definition. The chi-squared is the sum of k normal distributions squared, and where the normals are 0, 1 distributed. And then we have a chi-square distribution with k degrees of freedom. Here, k degrees of freedom, because we have k summons. All right, we will hold that thought. We will need it in a second. So we had assumed that epsilon I is distributed as normal 0 sigma. And I should call that Gaussian 0 sigma here. And then if I divide by sigma, a constant, then I get the normal distribution 0, 1, right? So standard normal distribution. The next thought, the ratio of the sums of squares to the estimated residuals and the true sigma squared is distributed as chi-squared. Here's our chi-square distribution. So why? Because, well, once I divide by sigma and squared here, I'm dividing by a constant. These are normal 0, 1, and I can rewrite these as sums of squares residual. This is the same thing, right? And then I know, because it's the sum of standard normals, we know it's chi-squared. Normally it would be chi-squared with n degrees of freedom because we have n summons. But in this case, we use some degrees of freedom up in estimating the means which are required to be known to compute the residuals. And we used p plus 1 parameters up to do that, the betas and the intercept beta. And therefore we lose some degrees of freedom here, so it's a chi-squared minus the degrees of freedom. Okay, so the expected value of a chi-square distribution equals its degrees of freedom. So we have the expected value of this quantity. And we can, because this is constant, we can multiply this out. So I have the expected values of the sums of squares equals to this. And now we're ready to derive the expectation of the sample variance. of sigma squared. So this is the definition, right? So this is just the same as that. It's just another way of writing it. That's the definition. So if I take the expected value of this, then this is constant, goes out in front. Expected value here we had on the last page, which is this times sigma squared. These canceled and it's sigma squared. So in other words, the expectation of the estimator of sigma squared comes out to be exactly sigma squared, and that means that the sample variance is unbiased, the sample variance being the estimator. So, of course, the only reason why we choose such a strange denominator, n minus the degrees of freedom, the degrees of freedom being strange, is to make the estimator unbiased. You would never think of that for any other reason. And yeah, the whole point is to make it out such that it's unbiased in the end. Okay. Now, individual betas. We had, or betas in general, we had seen that beta is distributed multivariate normal with mean beta, and this is the variance. Right? Sigma squared times the inverse of this matrix. Often, we just make an inference about one particular value of beta, not the whole vector at the same time. You could, but often we just are interested in individual betas. So if I just take one individual beta here, like the j is 1, then I have the multivariate, then I have just a normal distribution or Gaussian distribution with beta j here, right? So this is just one entry of the matrix, of the vector. And for the matrix here that I have here, I take the jth diagonal element of that matrix, and I factor out the sigma in here. Right? So because we have normal, we have a sigma squared here, the variance, and because I write Gaussian, it's not the variance, but it's the standard error. That's why we have a sigma squared here and a sigma there. And here we have the whole matrix, and here we have the square root of the diagonal element. Once we have this written as a Gaussian, we can standardize to make it Gaussian 0, 1. So I'm subtracting beta j and standardizing here through by the standard error, and then I have a standard normal Gaussian. Okay, now we know that the distribution of this expression is Gaussian. That means that the sampling distribution is t. Right? And t looks very much like a Gaussian. It just has heavier tails. And as n increases towards infinity, it converges towards the Gaussian. And this is also where it comes from, well, when it's roughly 30 to 50 observations, then more or less it is Gaussian. So this really only matters for very small numbers. Given that we now have distribution, we can construct this t-statistic. And it's a kind of statistic that happens over and over. We have the estimate minus a hypothesized value, and then we standardize them by the standard error. It's a distance type estimate, where this is a distance, the difference between the estimate and the hypothesized value, and we're just standardizing to be able to use the same distribution for different combinations here, different values. Having the distribution and the standardized statistics, we can now make hypothesis tests as usual for beta in this case. In Stat 231, you heard about a sort of rule-based 5-step hypothesis and procedure. And here we have formulator hypothesis, meaning beta 3 equals 3 or 5. And here we have estimate the value for from the data. Beta 3 actually turns out to be 7. Step 3, calculate the discrepancy measure. Well, 7 minus, let's say 5, is 2, and then I standardize that by the corresponding standard error. And then, based on how unusual that is with respect to the t-distribution, I then get the p-value from the tails, right? How unusual is that? And the larger values you have, or the larger negative values you have, the more unusual it is, the smaller the p-value, and then you interpret it. Okay, that concludes the end of this segment.